Welcome back to Physics Fundamentals. In this video, I want to talk about ideal gases. Up until this point, we have by and large studied solids in our study of physics. We've started to broach into liquids and gases. We've tried to avoid that because as you go from solid to gas, there's more that the material can do, right? A solid object pretty much just sits there. Maybe it rolls or spins or something like that. A liquid can slosh around, and a gas has anything it can do, right? Gases can be compressed, gases can be expanded. There's a lot of parameters that go into the behavior of a gas. The idea of an ideal gas is to try to avoid some of the complications, right? So an ideal gas is generally comprised of a single type of gas, right? So we'll deal with oxygen gas or nitrogen gas, and not necessarily ambient air, which is oxygen and nitrogen and other stuff. We will generally deal with gases at temperatures that are relatively near our temperature, right? Human body temperature, room temperature, environmental temperatures. Try to deal with gases that fall into there. We'll also deal with gases that are at a relatively standard pressure. And as long as we are vaguely within those constraints, the equations of an ideal gas are going to work perfectly fine. But before we can get there, I just mentioned this idea of pressure, which is not something we've really talked about previously. Pressure measures how spread out a force is. Right. So the equation here, pressure is force divided by area, and the units of pressure are the Pascal. Right. The symbol for Pascal is PA, yeah, 2 letters for 1 unit, and 1 Pascal is 1 Newton per square meter. The classic example of why pressure matters is a bed of nails. Right? If you step on a single nail, you're not going to be in for a very good time. But if you step onto a bed of nails where someone has hammered hundreds of nails as close together as possible on a board, well, it might not be pleasant, but you should be able to walk on it. Because when you have hundreds of nails under your foot, the head of each nail is only taking a small part of your weight. When there's only 1 nail under your foot, the tip of that 1 nail is taking your entire weight. So by spreading out the force, the amount of force on any 1 nail is not enough to puncture skin. If you're not spreading out the force, well, now your foot has a hole in it. Don't take this as advice. Please don't try walking on a bed of nails unless you are a professional or you happen to know one. All right. The most common form of pressure that we deal with is atmospheric pressure. We don't tend to think of it this way, but air is matter. And if air is matter, then it has mass. And if it has mass, then it has weight. And so if you think about the planet Earth, there is a huge column of air stacked on top of just about anything. And so the force of the weight gets spread out uniformly across the entire surface of the Earth, which means that pressure is a great way of representing that. Because of that, we've invented a unit of pressure called the atmosphere. And that's about the same as 100,000 pascals. It's more precise, but I'm not that worried about it for right now. Just understanding that there is this unit is important. And then if we want to go into the US customary system, in the US customary system, we tend to use a unit called the PSI, which stands for pounds per square inch. Right? In the US customary system, we use inches instead of meters, and we use pounds instead of newtons, so it makes sense. An inch is quite a bit smaller than a meter, so it makes sense that the PSI measure for atmospheric pressure is a lot smaller numerically than the SI unit in pascals. The particulars here aren't that important. We're actually never going to need to do a unit conversion for what we're dealing with, but I wanted to bring to your attention that there are these 3 units of pressure. One of the nice things about the formulas we're going to be working with is that as long as we keep a unit, we can be consistent with that unit, and we don't have to worry about which unit it is. I'm going to start off with Charles's law. Charles's law tells us that if pressure is held constant, then the ratio of volume to temperature is also constant. Oftentimes you see this written as V1 over T1 equals V2 over T2. So how do you keep the pressure of a gas constant? Well, one common apparatus, I say common, it's common in experiment and laboratory science classes than it is an actual practicality, but it absolutely does work. Right? Imagine a container with gas that has a sealed piston in it. Well, the mass of that piston is going to cause weight. And that weight will be distributed over the entire piston, which means that this gas is under some amount of pressure. If the volume of the gas changes, the piston will either raise or lower. And by raising or lowering the piston, we can change the volume without changing the pressure. Right? A somewhat smaller example of the same thing is in a combustion engine. Right? The pistons in an engine actually tend to work by changing the volume, but we can set it up in this way. It's just not quite as efficient. Up next, we have Boyle's law. Boyle's law tells us that if the temperature of a gas is held constant, then the product of pressure and volume is also constant. The equation here generally looks something like P1V1 equals P2V2. And I think holding temperature constant is a little bit easier to understand. Generally speaking, if we have a canister of gas, right, so we have pressure and volume allowed to change, which means that this canister has a piston in it that's allowed to move. But let's put that canister inside of an oil bath or a water bath that is kept at a constant temperature. Because the bath is kept at a constant temperature, any changes in temperature of the gas are transmitted into the bath, and then it transmitted from there into the environment. So in essence, the temperature stays constant. Right? And why have I not done an example of either of these equations? Because generally speaking, we put them all together in what's called the combined gas law. P1 V1 over T1 equals P2 V2 over T2. If you've previously taken a course in chemistry, you may have seen a different version of the combined gas law that says PV equals nRT, or maybe PV equals nKT, depending on which variables you happen to like to use. We're not going to get into that because this idea of N and R are a little bit beyond the scope of this course. All right. But the combined gas laws simplify into either of the laws that we've already talked about. If you happen to know that the temperature is staying constant, then T1 equals T2, multiply both sides of the equation by that temperature, and you get P1 V1 equals P2 V2. A canister of nitrogen gas is held at a constant pressure of 180 kilopascals. If the temperature starts at 18 degrees Celsius, how high should the temperature be raised to increase the volume from 1.5 liters to 1.8 liters? We know that the pressure is constant. We could write it down, but honestly, knowing the number is not important once we know it's constant, because we can divide both sides of the equation by that constant pressure and just get rid of it, so that we have V1 over T1 equals V2 over T2. Now the only variables we care about are V1, T1, V2, and T2. Our temperature starts at 18 degrees. Our ending temperature is unknown. Our volume starts at 1.5 liters and ends at 1.8 liters. And it feels like we can dive in and solve this problem, but unfortunately, we actually need to do a little bit more. It turns out that if you use a relative temperature scale, these equations don't work. As we mentioned when we talked about temperature scales, right? The difference between temperatures is meaningful, but multiplying or dividing by a temperature in a relative scale is meaningless. So we have to convert that 18 degrees Celsius into a Kelvin temperature, Remember that the conversion from Celsius to Kelvin is just add 273. So we get that the temperature here is 291 Kelvin. My volume is given in liters, and that's actually okay. We don't have to convert from liters to cubic meters or cubic centimeters or anything like that, because they are absolute volume scales. It's just a different unit. So because our volume is consistently in liters in both cases, we can stick with that. We can plug everything in, and we have 1.5 liters over 291 Kelvin equals 1.8 liters over our unknown temperature T2. We have here a proportion. We can solve a proportion using the cross product test. 1.5 times T2 is equal to 1.8 times 291. My calculator is happy to tell me that 1.8 times 291 is about 524. And then I can get T2 by itself by dividing by 1.5. So if I take that 524 and I divide by 1.5, my calculator tells me that comes out at about 349. All right. And this is going to be in Kelvin. Technically speaking, that's it and I'm done. But since I was given an initial temperature in degrees Celsius, I think it's probably worth giving a final temperature in degrees Celsius as well. Remember, from Celsius to Kelvin is add 273. From Kelvin to Celsius is subtract 273. And when I do that, I get about 76 degrees Celsius. All right, so unpleasantly hot, but not as hot as boiling water. Let's take a look at another example. The pressure gauge on a helium tank indicates that a 750 milliliter balloon was filled to 120 kilopascals in a 20 degrees Celsius room. This balloon is then compressed into a 600 milliliter canister in a walk-in freezer at -2 degrees Celsius. What is the relative pressure of the balloon now? First of all, let's think about this in general. We know that as temperature increases, a gas will expand. As temperature decreases, the gas will contract. So that's why the walk-in freezer is so important. By taking the balloon into the walk-in freezer and allowing that gas to cool down, it will shrink, which is going to make it easier to compress it into the smaller canister, although not a guarantee. The other thing, and probably the more important thing that's going on here, is that we're dealing with a relative pressure. It's not stated in the problem. This is something that you're expected to know, although I will do my best to remind you whenever it's coming up, because that's not what I'm testing you on. But when we're talking about relative pressure, when we're talking about a pressure gauge, it's talking about the difference between the pressure of the container and air pressure, right? So I will do my best to always remind you when I'm introducing a problem like this. Remember that air pressure is whatever number. And given that I'm using two significant digits everywhere, we'll call it 100 kilopascals. This 0 is significant, the other one is not. If I cared more, if we were doing something with more precision, we might look at a higher precision value of air pressure, and at that point it starts to change based on where you are, right? Air pressure at sea level, air pressure at elevation are different. air pressure on a hot day and air pressure on a cold day are different, right? The atmosphere is changing. We have weather, and that comes into play in the air pressure. But we're not going to worry about any of that. We're just going to deal with this on the general terms like this. And so, our initial pressure is not just the 120 kilopascals on the gauge. We have to add to that the 100 kilopascals of atmospheric pressure. The initial volume is 750. That is an absolute volume, nothing to worry about there. The initial temperature, again, 20 degrees Celsius. Celsius is a relative scale. We have to add the absolute zero temperature. Conversion from Celsius to Kelvin is add 273. P2, pressure at the end, that's unknown. That's what we're being asked for. Volume at the end is 600 milliliters. And temperature at the end is -2, but again, we have to add 273 to get a usable number. All right, so our initial pressure is 220 kilopascal. Our initial volume is 750 milliliters. Our initial temperature is 293 Kelvin. Our final pressure is still unknown. Our final volume is still 600 milliliters. And our final temperature is 271 Kelvin. And with all of that, P1 V1 over T1 equals P2 V2 over T2. I can rearrange and solve for P2 right away if I want to, and I think I will. Multiply both sides of the equation by T2. And divide both sides of the equation by V2 gives me P2 all by itself. Then from there, it's just a matter of plugging everything in. Pay close attention to your subscripts. Make sure you're putting the right one in the right place. And then be very careful how you're punching it into your calculator. I get 254.3, etc., but I'll round that to two significant figures and call it 250. But I'm not asked for the absolute pressure, I'm asked for the relative pressure, which means I have to subtract off atmospheric pressure. And the relative pressure of this balloon, if we had tried to hook the pressure gauge up to it after smashing it into the cylinder, would read 150 kilopascals. There are a lot of little things going on in that problem, a lot of little places to take your time, be careful, make sure you're understanding what's going on. The actual equations are very straightforward and also very forgiving, but making sure that you understand what the measurements are giving, make sure you understand when you have absolute measurements and when you don't, that can be a little bit confusing. Again, for temperature, you need to know that the Fahrenheit scale and the Celsius scale are relative temperatures. The Kelvin scale is an absolute temperature. You need an absolute temperature in order to use the gas law formulas. Pressure uses the same units, but how the measurement is set up can change. So pay attention to how it's stated in the problem. If it is talking about a relative pressure, it will say that. It might call it a gauge pressure, but it will say something to remind you that this is not just the absolute pressure that you need. Volume is nice. There's really no such thing as relative volume, so that's not something you ever have to worry about. And I think that's enough on this one, so I'll wrap up the video there. Thank you as always for joining me. I'll see you next time.